Good morning, everybody, or good afternoon, or good evening, depending on when you're watching this. We are starting chapter 13 today, your very first chapter in Chemistry 112. Now, chapter 13 harkens back to the chapter before this because we're going to depend on our study of intermolecular forces to help guide us when we look at how substances mix. So let's review intermolecular forces. Remember, intermolecular forces are the electrostatic attractions between ions, between molecules, and that have partial charges because of the polarity of the molecule, the interactions between molecules and ions, and the interactions between non-bonding atoms, like a neon atom for a neon atom. The intermolecular forces are responsible for gases condensing into liquids, liquids freezing into solids, and they're instrumental in how substances mix. So let's kind of remind ourselves, intermolecular forces are usually weaker than bonding forces, intramolecular forces. So bonding forces, intramolecular forces, are the electrostatic attraction between ions, or the electrostatic attraction of two nuclei for a shared pair of electrons, or the attraction of a nuclei of an atom for the electron C. So ionic bonding, covalent bonding, metallic bonding. These forces are responsible for holding compounds together internally, and they help determine the structure and the chemical properties of compounds. Okay, so they're larger charges over shorter distances, which makes stronger connections. Intermolecular forces, one more time. The electrostatic attraction between partial charges due to polarity of particles or induced polarity of particles, or the interaction between ions and molecules. Okay? Intramolecular forces, the bonding forces are usually relatively stronger because of the larger charges, shorter distances, and the intramolecular forces are usually weaker due to smaller charges and larger separations. Okay? Now, let's remind ourselves about what our intermolecular forces are. First one is a dipole-dipole. It's the attraction between polar molecules. Now, this is most important for highly polar molecules like ammonia or the water molecule. It can be seen when we have two identical molecules, so in pure substances, and dipole-dipole interactions are important when we are mixing molecules of different types. So water and ethyl alcohol interact through a dipole-dipole interaction. Okay? Hydrogen bonding. It's the attraction of a hydrogen bonded to an oxygen, nitrogen, or fluorine on one molecule with a lone pair of electrons on a nitrogen, oxygen, or fluorine in another molecule. This is a very site-specific interaction. That's why it's called hydrogen bonding, which is kind of a misnomer. It's very important in biological systems. It helps with the folding of proteins. It's important in the holding together of the two chains in the double helix in DNA. Hydrogen bonding can be seen between like molecules and in mixtures. Okay, and then London forces, also called dispersion forces, are attractions between temporary dipoles, or what we would call an induced dipole. The London force is the most prevalent intermolecular force there is. It exists between all types of particles, and it's the only intermolecular force at play between non-polar particles. So London forces can be seen in pure substances and between unlike molecules, and London forces depend on the polarizability of the molecule, atom, or ion. The larger the particle, the more elongated the particle, the more polarizable it is. Okay? So, let's remind ourselves a little bit about London forces and polarizability. So if we had argon atoms, if the argon atoms are far apart, their electron clouds are spheres. But when they get close together, you can get this temporary kind of egg shape to the electron cloud. Once one gets this kind of temporary egg shape, it can create a temporary egg shape where you have a slightly negative end and a slightly positive end in an argon that's near it. So if you get a whole bunch of them together, you get this temporary, I'll get back to where I'm going. You can get a lot of temporary dipoles. Now these are not permanent dipoles, this is temporary. It's kind of like holding your breath and sucking in your stomach to try to make it look flat. Can't do it for forever. These collapse and reform and collapse and reform. But they can interact. They're weaker dipoles, okay, they're not as strong a dipole, and they're temporary. Now, for molecules of the same mass, shape controls the size of the London force. Like I said, more elongated, stronger. It even is important when we have molecules that have a dipole-dipole interaction or a hydrogen bonding, because the closeness of one molecule to another can increase the polarity of a bond or a polarity of the molecule. Okay? So we're going to look at some pure substances. We're going to look at the structure of the molecules, and we're going to talk about polarity and what kind of intermolecular forces we're going to see. Okay, so let's start drawing some things. Now, let's start out with something like ammonia, NH3. Now, if you do the Lewis dot structure, looks like this. Okay, now when I look at this, I see that there are 4 groups around the nitrogen. One of them is a lone pair. So I know right off the bat that this molecule is going to be polar. Because if you think about drawing it, okay, 3D, we have a tetrahedral shape and we have trigonal pyramidal. Okay, so if we think about the way the electrons are going to be pulled, for each hydrogen bond, nitrogen is more electronegative. It pulls the electron density in. So we have a polarity like this. So since this molecule is polar, I know right off the bat that I can have dipole-dipole interactions between 2 ammonias. And everything's got a London force. Okay? So between 2 nitrogen molecules, ammonia molecules right now, I know that there's a dipole-dipole and there's a London interaction. Anytime you have a polar molecule and you have dipole-dipole, you have the possibility then of having hydrogen bonding. You want to look and see if you have hydrogens bonded to a nitrogen, oxygen, or fluorine. In this case, I have a hydrogen bonded to a nitrogen, so this can also hydrogen bond. So between 2 ammonia molecules, we see 3 different intermolecular forces at play. Now, if I were to draw in a second nitrogen of an ammonia here. Okay? This hydrogen here could interact with this lone pair. That's where our hydrogen bond comes from. Okay? If I just had nitrogens and they were kind of jumbly, okay, we could also think about this side of the nitrogen, the lone pair side, being attracted to the hydrogen base of this ammonia. That would be a dipole-dipole interaction. Okay? And the increase in this dipole, because these guys were close to each other, would be our London force interaction. All right? So that's an example of how we evaluate a molecule. Now, if I were to look at, let's say, methane. Okay, Lewis dot structure looks like this. CH4. I draw it in 3D. Looks like this. Okay, if I think about this, every group around the central carbon atom is the same. Because every group around the central carbon atom is the same, I know this is non-polar. If it is non-polar between two methanes, all I can see is the London force, also called dispersion. Okay? There is no dipole-dipole, there is no hydrogen bonding. I know I have hydrogens here, but they're bonded to a carbon. They're not bonded to an oxygen, nitrogen, or fluorine. Okay? Now, what if I had this molecule? Nitrogen trifluoride. Okay? It's our 3D drawing. There are 4 electron groups around that central nitrogen. One of them's different than the other. So I know right off the bat, I have dipole-dipole, because this molecule is polar. Okay? All right, now, everything's got a London force. The next question we ask is, can a nitrogen trifluoride hydrogen bond with another nitrogen trifluoride? The answer is no, because there are no hydrogens here. I have nitrogens and fluorines, but no hydrogens. So a nitrogen trifluoride can dipole-dipole interact with another molecule of nitrogen trifluoride, and it can London force interact with molecules of nitrogen trifluoride. Okay? All right, let's go back over. We're traveling. Okay, now, let's look at our intermolecular forces that we see in mixtures, and only in mixtures. There's the ion dipole. It's the attraction between an ion and a polar molecule, such as the attraction between a water molecule and a sodium ion, or a water molecule and a potassium ion, or a water molecule and a chloride ion, or a nitrate ion. For any salt to dissolve up in water, well, the ion dipole interaction has to be just about as good as the ionic bond, or just about as strong as the ionic bond. If the ionic bond is really strong compared to the ion dipole interaction that we can generate with water, then that ionic compound isn't going to dissolve well in water. So calcium carbonate, which makes the limestone, okay, caves, doesn't dissolve up that well in water. So that's why you get the stalagmites and the stalactites in a cave. I grew up in Kentucky, and we learn a lot about caves in Kentucky. Okay? There is the ion-induced dipole. It's the attraction between an ion and a non-polar molecule. And it depends on the polarizability of the non-polar molecule. It's important in things like iron 2+ ions binding oxygen in hemoglobins. right? It's not a super common intermolecular interaction, but it does have places where it's important. And then there is the dipole-induced dipole, which is the attraction of a polar molecule for a nonpolar molecule that has been polarized. The dipole-induced dipole interaction is what allows oxygen to dissolve up in water, nitrogen to dissolve up in water, carbon dioxide to dissolve up in water. I like my fizzy drinks. And so that's our list of our intermolecular forces. So what forces are at play between what molecules depends on the structure of the molecule, okay? And that means not only who's attached to who, but how everything plays out in 3D. All right, so let's look at some molecules and see how they're going to interact. So we're going to take different kinds of molecules. Sorry guys, you just got dropped. Okay, here we go. Now, water is a universal solvent. So let's think about trying to mix some things with water. So H2O, Lewis dot structure. Thinking about it in 3D, it's a planar molecule in that all of the atoms end up in a plane. Okay, so 3D it kind of looks like this. One of those electron groups is sticking out here, one is going back. So this is our slightly positive end and this is our slightly negative end of the molecule. Okay, let's think about trying to mix it with iodine and methanol, CH3OH. Okay, iodine, drawing its Lewis dot, looks like this. If I think about just the connections, okay, it looks like this. It's a linear 2-atom molecule. Now, what we know about water is that water is polar. Iodine is nonpolar. Okay, so between these two, so between water and iodine, what I can see is a London force, because between any two particles we can generate a London force, and I can get a dipole-induced dipole. Okay? If I look at water and methanol, now methanol kind of looks like this. If I was looking at it in 3D, and I'm just going to put OH there, talk about it in just a sec. Okay, it looks like this. Okay, now the hydrogen is going to extend off that oxygen. Okay, so if I wanted to, I could kind of think of this as being like, you know, have a triangle down. Let's see, put that one's that way. Let's see, trying to 3D this out. Hydrogen here. One pair there. Okay, looks something like that. Okay, when you look at this molecule is polar. So just like water, this molecule is polar. If you look at that carbon and think of it as your central atom, not all the groups around that are the same. If you look at this oxygen, it's got this carbon group, it's got the hydrogen, it's got 2 lone pairs, it's definitely not the same. This sucker is polar. So between water and CH3OH, okay, switch. I know that I can have dipole-dipole, and I can have London. And now I ask, can we hydrogen bond? Well, this has a hydrogen bonded to an oxygen with lone pairs of electrons. This has hydrogen bonded to oxygen with lone pairs of electrons, so we can also see hydrogen bonding. So between methanol and water, we can generate 3 intermolecular forces. Right? Between water and iodine, we can only generate 2. A London force and a dipole-induced dipole. And the dipole-induced dipole is much weaker than a dipole-dipole, much weaker than hydrogen bonding. Okay? So, back to our notes. All right, guys. Now, when we start making mixtures, we're talking about a solution. A solution is a mixture, okay? It's a homogeneous mixture, which means the mixture is happening on the atomic/molecular level, and it's where 2 or more substances are in physical contact with each other. They're not chemically bonded together, they're just physically hanging out. Now, anytime we have a solution, we break the components up into solute and solvent. You're going to have one solvent, everything else in there is going to be a solute. Now, the solute is the component or components of the solution that are usually present in smaller amount, may change phase. The solvent is the component of the solution usually present in larger amount and does not change phase. So we're going to watch out for words, okay? Soluble, insoluble, miscible. Soluble means that a specific substance will dissolve up in a given solvent. So sodium chloride is soluble in water, okay? Insoluble means a specific solute, okay, or substance will not dissolve up to any great extent in a given solvent. Water and oil don't mix, so we could say that oil is insoluble in water. Okay? Miscible means that they'll mix in any ratio. So, let's talk about solubility. A lot of these words say the same, sound the same, so you got to be careful. Solubility is the amount of solute maximum that can be dissolved up in a given amount of solvent or solution. Okay? So it tells you how much. The higher the solubility, the better a solute mixes with a solvent. Now, there are 2 factors at play when we look at solution formation. Okay? Mixing of 2 different substances. The change in enthalpy, heat energy, and entropy. Okay, now this is the first time we've talked about entropy. I have a bumper sticker on my office door that says entropy happens. So let's talk about entropy for a minute. Okay? Entropy is a measure of the possible ways the energy and particles in a system can be arranged. So, you know, a lot of people talk about entropy as being chaos, but it really has to do with ways things can be. Okay? So, if I had neon and argon in this chamber and there's this real thin membrane between them, okay? There is a certain number of ways that I can have these different neon arranged over here and these argons arranged over here. All right? Now, if we were to pull out the barrier, pop it, remove it somehow, the particles can then move back and forth from one side to the other. So if we do that, okay, think about if these argons were numbered and these neons were numbered, and think about the different ways that I could have them just in these positions with the numbers, you know, neon 1 here, neon 2 here, 3, 4, 5, 6, 7, 8. But now what if it was 1, 2, 3, 4, 5, 6, 7, 8? Once I remove that barrier, there's a lot more entropy because there's more ways for the particles to be arranged in this space. So this would be going from here to here, okay, from here to here, there's an increase in entropy. Increasing entropy happens spontaneously, and you get to a uniform solution. Okay? What we can say is that there's a pervasive tendency of energy to be spread out or dispersed. There is a pervasive tendency for particles to mix and intersperse. So if you think just about energy spreading out, think about putting one end of a piece of metal in a flame. Okay? That heat will travel up through the metal. If you're holding onto it with your bare hands, you're going to know it pretty quick. So the process of mixing increases the entropy of the system and is a driving force in mixing. So that we can say change in entropy, the symbol for entropy is S, is going to be positive when things mix. Now, the other factor is change in enthalpy. Now, you remember from last semester, enthalpy, change in enthalpy is sometimes called heat energy, and it can be endothermic or exothermic. Endothermic means that it's taking energy into the system. Exothermic means that it's releasing energy to the system. And whether enthalpy increases or decreases, okay, depends on whether we're making connections between atoms or particles or we're breaking connections. Okay? When we break connections, we have to absorb energy. When we make connections, we release energy. Now, remember that all particles ultimately are sticky, so that there can be attractions between the molecules, the dipole-dipole, the hydrogen bonding, the London force, the ion dipole. All of those are the sticky factors, okay, the attractions that we can have between particles. So when I mix things together, I'm changing who's stuck to who, okay? So when we mix two pure substances together, we first have to separate the pure substances one from the other. We have to break connections, takes energy, and then we allow particles that are not alike to stick to each other, to attract. That's going to release energy. Okay? So breaking attractions between particles, disrupting the intermolecular forces or intramolecular forces for ions takes energy. The process of separating particles is endothermic, delta H is positive. Forming new interactions between unlike particles releases energy. Exothermic, negative. So anytime we have a mixing process, we have some things that are going to require an input of energy. Some parts of the process are going to release energy. So the enthalpy of mixing depends on which is larger. If it takes more energy to separate pure substances than the energy released when you have interactions between unlike particles, then you have an overall process that's endothermic. And that mixing, when you mix those things, it would feel cool to the touch. If it is exothermic, then the amount of energy that you're using to separate like particles is less than the energy released when the unlike particles attract each other, and that would feel hot to the touch. If you mix ammonium nitrate in water, okay, and you hold it and you touch it, it's cold to the touch. If you've got a pre-bought first aid kit, it's going to have a chemical cold pack in there, and what it does is when you snap it, it actually releases like ammonium nitrate, well, usually, yeah, it could be ammonium nitrate, could be aluminum nitrate, into water, and as it mixes, the process of mixing is endothermic. To get them to mix, it has to absorb energy. So that's why it feels cool. A chemical warm pack, hot pack, okay, would mix two things that release energy when they're mixed. So the best mixing happens when the overall change in enthalpy is 0 or a negative value. So it's exothermic. Anytime you mix two different substances together, there's going to be an increase in entropy. So let's talk about breaking down and going through the steps of solution formation. Okay, so we have to separate particles of solute from solute. That's endothermic. You're breaking attractions. You got to separate particles of solvent from solvent. That's endothermic. Okay, again, energy absorbing. And then lastly, we form the attractions between solute and solvent in the mixing, and that's exothermic. So if the overall change adds up to 0 or negative when we look at the enthalpy, we usually have good solution formation. If we have a solution formation where the energy, the enthalpy is a large positive value, looking at what you can get out of this, then you're not going to have good mixing, and you're going to have a solute that is insoluble in the solvent, doesn't dissolve up to any great extent. So you see little or no mixing. If the value is just slightly positive, slightly endothermic though, you still could have good mixing, because remember our second factor is entropy, and entropy always increases when you mix things. Okay, so we have those two entropy factors. Now thinking about it pictorially, okay, we have solvent-solvent interactions, we have solute-solute interactions, and then we're going to have solute-solvent interactions. We want this interaction to be about as good or better than these so that I can get good mixing. Okay? So we can look at it qualitatively, okay, and we've kind of already done this, but let's run through it and see how you can do here. So if I have ammonia and water and I want to think about them mixing, okay, ammonia is polar. Water is polar. So that's good right off the bat. They're both polar molecules. So between them, I know I can see dipole-dipole. So we're going to have dipole-dipole. Now, I also know that there is London, because any two molecules can interact through a London force. Next, I want to see if I can get hydrogen bonding. Well, nitrogen here in ammonia has 3 hydrogens bonded to it in a lone pair, and I have hydrogen bonded to oxygen here, so I can also have hydrogen bonding. So ammonia and water ought to mix pretty well, because between ammonias I see dipole-dipole hydrogen bonding and London forces. Between water molecules I see dipole-dipole hydrogen bonding and London forces, and I can see those 3 in the mixture. Least an even trade. Okay? And then I get that bump up from entropy, we're golden. Now, here we have ammonia, okay, which we know is polar, and in between ammonia molecules we know we have London, we have dipole-dipole, which I'm just going to abbreviate DP-DP, and we have hydrogen bonding. Now when I look at this molecule, it's all carbons and hydrogens. So this guy is nonpolar. Okay? So in our pure substance, all we have are London forces between the two. Okay? I know there's going to be a London force because every interaction can have a London force. But now I have a polar molecule and a nonpolar molecule. So I have dipole induced dipole. Now, if we look at this, ammonia has it has a strong dipole-dipole, it has strong hydrogen bonding, it's got the London. This only has London. Going to a dipole-induced dipole and a London force might improve the situation with this guy, but for ammonia, it's giving up some very strong interactions for weak interactions. So these two aren't going to mix very well. So up here I have good mixing, down here I have poor mixing. Because what ammonia is giving up to mix with the pentane molecule is nothing compared to what it can have between two ammonias. So overall, this would be an endothermic mixing process, and probably a large endothermic. This is going to be exothermic. Okay, so let me erase here. And let's scroll up. So just kind of remember the general statement, like dissolves like. The more alike the two substances are before we try to mix them, the easier they're going to mix. So if you look at the list of intermolecular forces that you can see between the two in pure substance, okay, then if they match very well, you're going to have good mixing. The more different they are, the poorer the mixing. So if I started thinking about mixing sodium chloride with hexane, oil with water, oil with hexane, and salt with water, okay, I have an ionic compound here and a nonpolar molecule. Poor mixing. Nonpolar molecule, polar molecule. Poor mixing. Nonpolar molecule, nonpolar molecule, good mixing. Ionic water. Well, I have an ionic compound and I have polar water molecules. I can generate an ion dipole. So if this is table salt sodium chloride, this is going to mix pretty well. Okay, so, you know, the biggies, dispersion, dipole-dipole, hydrogen bonding, ion dipole. Okay, those are the biggies you're going to see most often. Okay, now looking at this kind of list here, kind of looking at some examples. Methanol, ethanol, 1 propanol, 1 butanol, 1 pentanol, 1 hexanol. Okay? What's happening here is the length of the carbon chain is increasing. These black circles are our carbon chain. The red is our oxygen, the blues are hydrogen. Okay? Methanol is very small, so it's polar, and there's a large part of the molecule that can interact with water. So it's very water soluble, it's polar, it can hydrogen bond, water soluble, very low solubility in hexane because it's polar. Okay, when I get to ethanol, it still mixes well with water, but its solubility in hexane has gone up because there's a larger portion of the molecule that's carbon chain. Okay? Propanol will mix equally in both, but notice the carbon chain is growing. When I get to butanol, which has 4 carbons, Notice the solubility in water is now very low, where it's very soluble in hexane. It only has this kind of end of the molecule that's showing polar nature. This end of the molecule is nonpolar. This is a split personality molecule. It's kind of a Jekyll and Hyde. It's got a polar side and a nonpolar side. Okay? And as the chain gets longer, the ability to dissolve up in water goes down because more and more of the molecule is unable to hydrogen bond with water, and it's non-polar. So the polarity of this thing decreases. Okay? So, we've been talking about this quantitatively. You could look at this we've looked at it qualitatively, we could look at this quantitatively, and we could add up the delta H's for solute separation, solvent separation, and mixing, and get the delta H for solution formation. Okay? So, pictorially, if we were to look at things in an exothermic process, separating solvent molecules solute from solute, spacing them out. Notice how it's nice and organized here, more chaotic here. Separating solvent from solvent, those are always endothermic processes. Mixing is exothermic, and notice from where I began to where I end, it's lower, so overall exothermic. This would be an endothermic example. Okay? So let's think about table salt for a minute. When we look at mixing table salt, sodium chloride, and water, to dissolve up in water, you actually have to break the ionic bond. Now, you separate water molecules from water molecules, and then you've got to separate sodium ions from chloride ions, and then you have to have sodium ions interacting with water and chloride interacting with water. Okay? So, some of these things are sometimes hard to measure separately. So, when you're talking about salts dissolving up in water, they talk about the delta H of solution being the energy change when the ions separate, when you're breaking the ionic bond, and the energy change when the ions get or interact with the water molecules. Okay? Now, we're not going to, sometimes I beat us over the head with looking at adding things up, but I don't think we're going to do it this time. I just want to run through this one example with you. Okay? Sodium chloride in water has a delta H of solution of 3.7 kilojoules per mole of sodium chloride that dissolves up. Now notice this is slightly endothermic, okay, not a very large kilojoule value. Sodium chloride, we know, dissolves up well in water, and that's because of the entropy change. And we're going to look at the entropy change here in a second. Sodium hydroxide dissolves up well in water. It has a delta H of minus 44.3 kilojoules. Exothermic, perfect. Ammonium nitrate has a positive delta H, but it's not huge still. It probably doesn't dissolve, well, it actually dissolves up fairly well in water, but it's still pretty small. Okay? One positive ion, like a sodium ion, is going to be surrounded by 6 water molecules with the oxygen side closest to that ion, because the oxygen side of the water molecule is the slightly negative end. These water molecules essentially become the entourage for this positive ion. Okay? They become waters of hydration, and they form what are called coordinate covalent bonds. These guys pretty much attach themselves to this sodium ion and then interact with the rest of the water molecules. Okay, so notice that these water molecules are hydrogen bonding to all these other water molecules. Okay? So, your general outline of why solutions form. Solutions form because there is a enthalpy advantage to being mixed, and there's an entropy advantage to being mixed. Okay? So when we talk about solutions that form, we can talk about a solution being unsaturated, saturated, or supersaturated. Saturated means that the solvent has exactly the maximum amount of solute it can hold at a given temperature. If more solute is added, it won't dissolve up. It'll just sit as a solid at the bottom of the container, and a dynamic equilibrium is established. Now, when we talk about dynamic equilibrium, okay, so my little black dots here are the solute dissolved up in the solvent. Okay? When I have put in, and when I dumped in some extra solute, it just ends up sitting as solid on the bottom. For every particle that jumps from that solid and tries to dissolve up, one from the liquid comes down, hits that, and gets stuck. So the concentration, or the number of particles up here in the solution phase, don't change. Okay? We can represent that by saying solute, solid, double arrow, because things are going back in both directions, solute, dissolved. Okay? Number of particles here, number of particles here don't change. Now, if you have a saturated solution, substance, all we have are London forces between the two. Okay? I know there's going to be a London force, because every interaction can have a London force. But now I have a polar molecule and a nonpolar molecule. So I have dipole induced dipole. Now, if we look at this, ammonia has it has a strong dipole-dipole, it has strong hydrogen bonding, it's got the London. This only has London. Going to a dipole-induced dipole and a London force might improve the situation with this guy, but for ammonia, it's giving up some very strong interactions for weak interactions. So these two aren't going to mix very well. So up here I have good mixing, down here I have poor mixing. Because what ammonia is giving up to mix with the pentane molecule is nothing compared to what it can have between two ammonias. So overall, this would be an endothermic mixing process, and probably a large endothermic. This is going to be exothermic. Okay, so let me erase here. And let's scroll up. So just kind of remember the general statement, like dissolves like. The more alike the two substances are before we try to mix them, the easier they're going to mix. So if you look at the list of intermolecular forces that you can see between the two in the pure substance, okay, then if they match very well, you're going to have good mixing. The more different they are, the poorer the mixing. So if I started thinking about mixing sodium chloride with hexane, oil with water, oil with hexane, and salt with water, okay, I have an ionic compound here and a nonpolar molecule. Poor mixing. Nonpolar molecule, polar molecule. Poor mixing. nonpolar molecule, good mixing. Ionic water. Well, I have an ionic compound and I have polar water molecules. I can generate an ion dipole, so if this is table salt sodium chloride, this is going to mix pretty well. Okay, so, the biggies, dispersion, dipole-dipole, hydrogen bonding, ion dipole. Okay, those are the biggies you're going to see most often. Okay, now, looking at this kind of list here, kind of looking at some examples, methanol, ethanol, 1 propanol, 1 butanol, 1 pentanol, 1 hexanol. Okay? What's happening here is the length of the carbon chain is increasing. These black circles are our carbon chain. The red is our oxygen, the blues are hydrogen. Okay? Methanol is very small, so it's polar, and there's a large part of the molecule that can interact with water. So it's very water soluble, it's polar, it can hydrogen bond, water soluble, very low solubility in hexane because it's polar. Okay, when I get to ethanol, it still mixes well with water, but its solubility in hexane has gone up because there's a larger portion of the molecule that's carbon chain. Okay? Propanol will mix equally in both, but notice the carbon chain is growing. When I get to butanol, which has 4 carbons, notice the solubility in water is now very low, where it's very soluble in hexane. It only has this kind of end of the molecule that's showing polar nature. This end of the molecule is non-polar. This is a split personality molecule. It's kind of a Jekyll and Hyde. It's got a polar side and a non-polar side. Okay? And as the chain gets longer, the ability to dissolve up in water goes down because more and more of the molecule is unable to hydrogen bond with water, and it's non-polar. So the polarity of this thing decreases. Okay? So, we've been talking about this quantitatively. You could look at this we've looked at this qualitatively, we could look at this quantitatively, and we could add up the delta H's for solute separation, solvent separation, and mixing, and get the delta H for solution formation. Okay? So, pictorially, if we were to look at things in an exothermic process, separating solvent molecules solute from solute, spacing them out. Notice how it's nice and organized here, more chaotic here. Separating solvent from solvent, those are always endothermic processes. Mixing is exothermic, and notice from where I began to where I end, it's lower, so overall exothermic. This would be an endothermic example. Okay? So let's think about table salt for a minute. When we look at mixing table salt, sodium chloride, and water, to dissolve up in water, you actually have to break the ionic bond. Now, you separate water molecules from water molecules, and then you've got to separate sodium ions from chloride ions, and then you have to have sodium ions interacting with water and chloride interacting with water. Okay? So, some of these things are sometimes hard to measure separately. So, when you're talking about salts dissolving up in water, they talk about the delta H of solution being the energy change when the ions separate, when you're breaking the ionic bond, and the energy change when the ions get or interact with the water molecules. Okay? Now, we're not going to, sometimes I beat us over the head with looking at adding things up, but I don't think we're going to do it this time. I just want to run through this one example with you. Okay, sodium chloride in water has a delta H of solution of 3.7 kilojoules per mole of sodium chloride that dissolves up. Now notice this is slightly endothermic, okay, not a very large kilojoule value. Sodium chloride, we know, dissolves up well in water, and that's because of the entropy change. And we're going to look at the entropy change here in a second. Sodium hydroxide dissolves up well in water. It has a delta H of minus 44.3 kilojoules. Exothermic, perfect. Ammonium nitrate has a positive delta H, but it's not huge still. It probably doesn't dissolve, well, it actually dissolves up fairly well in water, but it's still pretty small. Okay? One positive ion, like a sodium ion, is going to be surrounded by 6 water molecules with the oxygen side closest to that ion, because the oxygen side of the water molecule is the slightly negative end. These water molecules essentially become the entourage for this positive ion. Okay? They become waters of hydration, and they form what are called coordinate covalent bonds. These guys pretty much attach themselves to this sodium ion and then interact with the rest of the water molecules. Okay, so notice that these water molecules are hydrogen bonding to all these other water molecules. Okay? So, your general outline of why solutions form. Solutions form because there is a enthalpy advantage to being mixed, and there's an entropy advantage to being mixed. Okay? So when we talk about solutions that form, we can talk about a solution being unsaturated, saturated, or supersaturated. Saturated means that the solvent has exactly the maximum amount of solute it can hold at a given temperature. If more solute is added, it won't dissolve up. It'll just sit as a solid at the bottom of the container, and a dynamic equilibrium is established. Now, when we talk about dynamic equilibrium, okay, so my little black dots here are the solute dissolved up in the solvent. Okay? When I have put in, and when I dumped in some extra solute, it just ends up sitting as solid on the bottom. For every particle that jumps from that solid and tries to dissolve up, one from the liquid comes down, hits that, and gets stuck. So the concentration, or the number of particles up here in the solution phase, don't change. Okay? We can represent that by saying solute, solid, double arrow, because things are going back in both directions, solute, dissolved, okay? Number of particles here, number of particles here don't change. Now, if you have a saturated solution, you can have the situation where you have exactly the number that'll fit. Okay, so in my classroom, if you were in here with me, there are 24 chairs. If I had 24 students, my classroom would be saturated. If another student were to try to join the class, somebody would have to leave the class. Or if somebody wanted to come in and sit down in the room, somebody would have to leave the room. Okay? That's still saturated. If I was saturated, and another example of saturated is if I had 28 people in this room and only 24 seats. So I would have all the seats filled and the other people would have to be standing up. Okay? Somebody got out of their chair, you could swoop in and check it. So every time somebody got up from a chair, somebody sat down in the chair, the number of people standing up, the number of people sitting would be the same. Both situations are saturated. Okay. In an unsaturated solution, there's room for more solute in solution. The solvent can hold more solute. So 24 chairs in my room, 15 students, unsaturated. Supersaturated solution means that the solvent is actually holding too much solute and is very unstable and a precipitation will occur. Solid's about to fall out of solution. So 24 chairs, 28 students, some students sitting in other students' laps. We know that's not going to last. Okay? Another possibility is that the components of the solute solution and the solute and the solvent are miscible, which means they will mix in any ratio. Water and ethyl alcohol, water and methanol are miscible. They'll mix in any ratio. For situations where things are not miscible, where there is a limit to how much solute can dissolve up in a given amount of solvent, we talk about solubility. Okay? Solubility is the concentration of solute in a saturated solution. Therefore, we need to remind ourselves about how we calculate concentrations, how we express concentrations. So let's remind ourselves, what's concentration? Concentration is the amount of solute per given amount of solvent or solution. Now, in chemistry, like you learned last semester, the most common way to express concentration is molarity. Okay? So let's remind ourselves, what's molarity? Molarity is moles of solute over volume of solution in liters. Now, remember that moles of a material A is equal to mass of A divided by the molar mass of A, or I could say moles of A is mass of A times 1 mole over how many grams are in a mole. So we're going to look at a couple of problems to kind of review about how to calculate molarity. Now you've already done it. I know this is review, but it's always good to make sure that everybody is on the same page. So we're going to look at problem 48 on page 577. Okay? Give me a second, guys. I have to switch over and I have to walk across the room to do it. Okay, this is our textbook. Okay, so let's look at problem 48 here. It says an aqueous potassium nitrate solution is made using 72.5 grams of potassium nitrate diluted to a total solution volume of 2 liters. Okay? It says calculate the molarity. Molarity is the only one we're going to worry about right now. Okay, now I know that I've got 72.5 grams of potassium nitrate and I have a volume of solution of 2.00 liters. And we're asked molarity. Okay, let's slide over here. So that I have board space. So, if I kind of break this down into steps, step 1 is I need to go from grams of potassium nitrate to moles of potassium nitrate. For this, I need molar mass. So 1 mole of potassium nitrate. Now, let me grab my calculator, because we're going to have to add some stuff up. So 1 mole of potassium has a mass of 39.0983 plus 1 mole of nitrogen, 14.0067 plus 3 times 15.9994. So 1 mole of potassium nitrate has a mass of 101.1032 grams. So 72.5 grams of potassium nitrate times 1 mole of potassium nitrate for every 101.1032 grams potassium nitrate gives me 0.717 moles of potassium nitrate. 3 significant figures here, 3 significant figures here. My molarity then is going to be my moles, KNO3, over volume of solution, and that has to be in liters. So 0.717 moles over 2.00 liters is 0.359 molar, or you could write moles per liter. Three significant figures here, 3 here, 3 here. Okay. Not too bad, right? A good reminder of things that we've already done, or things you've already done. All right. Now, just to kind of remind you, when we're making solutions, sometimes a direct approach is not always practical. Sometimes it's hard to weigh out the amount of sol you need to make a specific solution because the amount of sol you need is so small. Back in my lab work days, I had to make on a regular basis concentrations of solution that were 1 times 10 to the minus 9 moles per liter. I mean, if I was shaky that day because I drank too much caffeine or I sneezed, the amount of material I was to weigh out was gone if I had to make that solution directly. So what we usually do in a case like that is we make a solution of higher concentration, and then you go through a dilution process to make solutions of lower concentration. So when we make high concentration solutions, we often call them stock solutions. Okay? And we can dilute stock solutions down to make less concentrated solutions. Now, we're going to be doing a lot of dilution calculations in lab. So understanding dilution is important when you want to look at how you're setting the stage for a chemical reaction to happen. So this isn't something to blow off, guys. This is something you're going to use over and over and over again. So it's important. Okay? when we do dilution, molarity of the initial solution times volume of the initial solution equals molarity final solution volume of final solution. Now let me kind of write some stuff in here. Okay, so when I look at this, molarity initial, oh here, let me erase. Molarity initial solution times volume initial solution. What I get is moles of solute. Okay? And that has to equal molarity of final solution, volume of final solution, because molarity times volume always equals moles of solute. Let me give you a for instance. My 24 students sitting in my chairs here in my classroom. If I walk from my room, which is 2311, down to the big lecture hall, 2255, which has 150 seats in it, okay, here I'd have 24 students in 24 seats. There I'd have 24 students in between 150 seats. My students would be more dilute. They'd be spread out more. Okay? We all know about social distancing nowadays. But my number of students, my solute particles, wouldn't change, I hope. Okay? But molarity initial, volume initial equals molarity final, volume final. Now the nice thing about this kind of calculation is that it doesn't matter what volume unit I use as long as the volume units match. So let's erase this. And we're going to look at problem 50 at the end of the chapter. Okay guys, let's look at problem 50 there. It says, to what volume should you dilute 125 milliliters of an 8 molar copper 2 chloride solution so that 50 milliliters of the dilute solution contains 4.67 grams of copper chloride? Okay, now they're being kind of tricky here. So let's not let their trickiness get in the way of us doing the problem. Now let's look at it. It says, what volume of a dilute, should you dilute 125 milliliters in 8 molar copper chloride solution so that 50 milliliters of the diluted solution contains 4.67 grams of copper chloride? So what we're asked in this is to find a V final. Now, we're given that our initial solution is 8.00 molar and that we have 125 milliliters. So we have molarity initial and we have volume initial. For our final solution, okay, we are given that we want to have 4.67 grams of copper 2 chloride in a volume of 50 milliliters. So if we think through this problem, really what they're giving us here, okay, when they give us a volume of the diluted solution and how much copper 2 chloride we want in it, they're giving me the concentration. But they're just not giving it to me in molarity. So if I start breaking this problem down, I'm going to switch out batteries before I run out, and then we'll do this problem. So give me just a sec here, guys. Okay, I'm back. Batteries changed. All right. So if we think about this in terms of steps, or parts. Part 1, I need to find what molarity final should be. So I'm going to go from the 4.67 grams of copper 2 chloride to moles of copper 2 chloride. So 4.67 grams, 1 mole of copper 2 chloride. I need the molar mass. So 2 times 35.453 plus 63.546. So there's 134.452 grams of copper 2 chloride for every 1 mole. So this is 0.0347 moles. Okay? The molarity here then is going to be 0.0347 moles for every 0.0500 liters. Because it told me that this solution, we wanted in 50 milliliters, combining that to liters is 0.0500. So 0.695 molar. Okay? Now, that was part 1. Part 2. Find V final for solution 2. So our molarity initial, volume initial has to equal molarity final, volume final. Our molarity initial was 8 molar. The initial volume, we're using 125 milliliters. That has to equal the final molarity, 0.695 molar, V final. So 8 times 125 divided by 0.695, 8 times 125 divided by 0.695, I get V final to be 1.44 times 10 to the 3 milliliters. 1.44 times 10 to the 3 milliliters. So 1,440 liters. Well, milliliters. Okay? So there was a hidden part embedded in this problem. You first had to figure out what molarity you needed for the second solution before you could figure out what volume you needed to dilute to. Now, let's talk about what we're going to face with dilution when we're doing lab. Okay? Here's something that you can find in the real world. What is the concentration of sodium chloride and potassium nitrate if 15 milliliters of a 0.1 molar sodium chloride solution is mixed with 20 milliliters of a 0.2 molar potassium nitrate solution? Now, this is what's going to happen when we mix 2 solutions together to start a chemical reaction. We're going to have solutions of known concentrations, and when we mix them together, we know we're diluting because we're increasing the volume once we've mixed the 2 solutions together. So let's look at it. Okay? All right. Get everything erased here. Okay. we are given that we have 15 milliliters of a 0.10 molar sodium chloride solution, and we have 20 milliliters of a 0.20 molar potassium nitrate solution. After mixing, the new volume would be 35 milliliters. 15 plus 20, 35. So for the NaCl, molarity initial 0.10 times volume initial 15 milliliters has to equal molarity final times 35 milliliters. So 0.1 times 15 divided by 35. The molarity final here is 0.043 molar. For the potassium nitrate, it's going to be the initial molarity, 0.20 molar, 20 milliliters, has to equal molarity final times the 35 milliliters. So 0.2 times 20 divided by 35. Molarity final here is 0.11 molar. Okay? Now that's the kind of problem and that's the kind of situation you're going to see in lab. Okay? All right, now let's slide back over. Molarity is the most common way to express concentration in chemistry, but it's not the only way. We can have mass percents, we can have volume percents, we can have mass volume percents. So, mass of solute divided by total mass of solution times 100% would be a mass percent. Volume of solute over total volume of solution times 100 gives you volume percent. Or mass of solute in grams divided by volume of solution in milliliters times 100 would give you mass volume percent. Chemists don't use mass, volume, mass, volume that often. We deal in moles of things looking at chemical reactions, so these aren't super convenient. I don't sweat these too much. Okay? Now, mole fraction is sometimes used. Symbol for mole fraction is X. So the mole fraction of A would be moles of A divided by the total number of moles of particles. When you're doing there's some very specific situations where you're looking, let's say, at the Henry's law, looking at a gas dissolving up in liquid where mole fraction is important. But this is such a simple calculation, I'm not going to bore you with it. Okay? Now, the last way to express concentration that we're going to talk about and we're going to work with is molality. Okay? Now, molality is important because molality is moles of solute over kilograms of solvent. Molarity involves volume of solution, okay? And because molarity involves volume solution, as temperature changes and the volume of solutions change slightly because things expand as they warm up and they contract as they cool off, molarity changes slightly with temperature. Molality, which is moles of solute over kilograms of solvent, moles of solute, kilograms, mass of solvent, doesn't change with temperature. So molality for a solution is the same whether you're at 70 degrees C or you're at 20 degrees C. Okay? So we're going to look at calculating molality. We're going to look at problem 60 on page 578, we're going to look at parts A, B, and D. So let's look at the problem. Look at problem 60 here. It says a solution is prepared by dissolving 20 milliliters of methanol, CH3OH, in 100 milliliters of water at 25 degrees C. The final volume of the solution is 118 milliliters. Okay? The density of methanol and water at this temperature are 0.782 grams per milliliter and 1 gram per milliliter respectively. So for this solution, we're going to calculate molarity, molality, and we're going to calculate mole fraction. Okay, it gives a little practice on all of those. So let me write down everything we've got while you're looking at this, and then we're going to work the problem. So we've got 22.2 milliliters of the methanol, CH3OH, and we've got 100 milliliters of water. Okay, for the methanol, density equals 0.782 grams per milliliter, and for the water, density equals 1.00 grams per milliliter. So let's okay. Now, part A, we're asked to calculate molality. Molarity. Big M. So molarity is going to equal moles of CH3OH, that's our solvent, over volume of solution. Now, we were also told that the total volume was 118 milliliters. Now, notice that we mixed 20.2 milliliters with 100 milliliters and we got 118. If you think about, you look at that and you go, well, no, that doesn't add up. Well, that's because when they mix and they interdisperse, they don't get the same volume as if I poured a water sample on top of a water sample. So that's why the total volume is a little bit less. It's the way they intersperse. They don't sit one right on top of the other. Okay? So if I look at this, my step one is going to be to calculate moles of CH3OH. Now, I've got density and milliliters. So I'm going to first, kind of as A, I'm going to get mass of CH3OH. So 20.2 milliliters times 0.782 grams per milliliter. So 20.2 times 0.782 gives me 15.8 grams of CH3OH. Now my calculator's reading 15.7964. Okay? If I round it to 3 significant figure, that's where I get that. So I'm going to go with the 15.8 grams CH3OH, 1 mole of CH3OH, and get the molar mass, I'm going to take 12.011 plus 4 times 1.0079 plus 15.9994, and it's 32.042 grams. So notice grams and grams divide out. And I get 0.493 moles of CH3OH. Okay? Step 2 then, to calculate the molarity, I'm just going to take my moles, 0.493 moles of CH3OH, and divide it by the total volume in liters, which is 0.118 liters. Okay, 0.493 divided by 0.118 is 4.18 moles per liter. Okay, now if you think about this total volume, there's 1 liter for every 1,000 milliliters. That's where I got the 0.118 liters from. Okay, so I've got the molarity. Part A is answered. Now if we look at part B, it wants molality. Molality uses a lowercase m as the symbol. Molality is going to be my moles of CH3OH over kilograms of water. Now I've already got my moles of CH3OH, my methanol, but I need my kilograms of water. So my mass of water is going to be 100 milliliters times 100 grams for every 1 milliliter. And then I know that there's 1 kilogram for every 1,000 grams. So notice milliliters and milliliters divide out. Grams and grams divide out. I'm going to be in kilograms. So 100 times 1 divided by 1,000 gives me 0.100 kilograms. So our molality is 0.493 moles CH3OH divided by 0.100 kilograms of water. So 0.493 divided by 0.1 is 4.93 little m for molality. So 4.93 little m. Now, if we look at mole fraction here, so if I go and look at D, my mole fraction would be moles of CH3OH divided by moles of CH3OH plus moles of water. Well, I've got my moles of CH3OH. That's 0.493. I don't have my moles of water though. So to get my moles of water, it's going to be our volume of water, 100 milliliters, times 1 gram for every 1 milliliter, times 1 mole of water for every 18 grams of water. Okay? So 100 times 1 divided by 18 So I have 5.56 moles of water. So our mole fraction here is going to be 0.493 over 0.493 plus 5.56. And I get 0.08, let's see, everything goes 3 significant figures, so 815. And since it is moles over moles, this has no unit. Okay? Now, remember, always think about breaking things down into baby steps. Analyze your problem thoroughly before you attempt to do it. Okay? The more analysis you put in before you put numbers on the page and try to plug them into things, the easier it's going to be for you. All right, now back to our notes. Travel across the space again. Now, molality is used when we're doing experiments that involve temperature change, because remember, as temperature changes, like I said earlier, things expand and contract, and the molarity changes with temperature, whereas molality doesn't. So when we start talking colligative properties, previews of coming attractions, we're going to run into molality. Okay? So solubility, mentioned it before, is a measure of the ability of a solute to dissolve up in a given solvent. It's expressed in terms of concentration of the solute in a saturated solution, most often expressed in terms of grams per milliliter or molarity. Okay? The more soluble a solute is in a given solvent, the higher its solubility is going to be. Now, there are several factors that affect solubility. The most important is the nature of the particles. Okay? Remember, like dissolves like, so the more alike the particles are, the better they're going to mix, the more soluble the solute is going to be in the solvent. We don't have control over the nature of the particles. Okay? But there are other factors that we can manipulate to affect solubility. One of the factors that we can manipulate is temperature. Okay? As you change temperature, you change solubility. Because remember, the dissolving process involves either absorbing or releasing heat energy. When I change temperature, if I increase the temperature, I am pumping heat energy in. If I decrease the temperature, I'm pulling heat energy out. So for solids and liquids, dissolving up in a liquid solvent, it depends on whether the dissolving process is endothermic or exothermic. If the dissolving process is exothermic, increasing the temperature actually decreases solubility. And decreasing temperature will increase solubility. So sodium hydroxide dissolving up in water is very exothermic. If I want a lot of sodium hydroxide dissolved up in water, I'd want my water to be at a lower temperature, and I'd want to have it in an environment where I would have the ability of sucking that heat energy out as it was being produced. So lower temperatures increase the solubility if you have an exothermic mixing process. If you have an endothermic mixing process, increasing temperature increases solubility, and decreasing temperature decreases solubility. So let's look at a pretty graph here. It shows the solubility as a function of temperature for several different salts. Now notice for sodium chloride, the line is almost level. And that's because the process of dissolving sodium chloride up in water is endothermic, but just barely. Okay? Goes up a little bit as you increase temperature. But notice for sodium nitrate, potassium chloride, potassium chlorate, increasing temperature increases solubility, which tells me then that the mixing process of those salts with water is endothermic. Now, notice that cesium sulfate here, the solubility goes down and levels off as you increase temperature. What that tells me is the process of cesium sulfate dissolving up in water is exothermic. So as I increase temperature, I decrease solubility. Now, for gases dissolving up in water, the process from an endothermic perspective is always exothermic. And on top of that, when I dissolve a gas up in water, we actually decrease the entropy. So increasing temperature when I'm trying to dissolve a gas up in water always results in a decrease in solubility. And a decrease in temperature increases the solubility. So as temperature goes up, the solubility of a gas goes down. As temperature goes down, the solubility of a gas goes up. So if you were a little fishy trying to breathe in the oceans, and you needed lots of oxygen, you are actually happier at the North Pole and the South Pole where the water is cold. You won't want to live at the equator where the water is warm. Now, if any of you guys have fishing ponds down here in Alabama, lots of times they will stock them with trout in December, for December, January, February, into March. If you don't fish those trout out and eat them by, let's say, June, all your trout are going to start going belly up in your pond, because as the water warms up, the concentration of oxygen goes down, and trout are very sensitive to water oxygen concentrations. Okay? Now, for gases, pressure also plays a role in solubility. So as pressure goes up, solubility goes up, and as pressure goes down, solubility goes down. Think about popping the top on a soda. You immediately hear it fizz. And that's because the carbon dioxide that makes your soda fizzy was dissolved up in that water under about 4 atmospheres of pressure of carbon dioxide. When you open it up, the partial pressure of carbon dioxide over the top is much less. So immediately it changes the solubility, and that stuff starts to come out of solution. Okay? So it's in equilibrium. X number of particles here, X number here. As you increase the pressure, you have more collisions up here than from the bottom, kind of at the barrier, and it starts to dissolve up more until you get this new equilibrium where you have more particles dissolved in the liquid. So increase the pressure, increase the solubility. Okay, I was just talking about it. So the CO2 pressure is released. You've decreased it over the top, and it starts to come out of solution, and it fizzes out. So this is where we hit Henry's law. The solubility of a gas in a liquid is equal to Kh, which is called a Henry's law factor, times the pressure for that gas. So for oxygen, it's 0.13 times 10 to the minus 3. For carbon dioxide, it's 3.4 times 10 to the minus 2. Ammonia, 5 times 10 to the 1. Helium, 3.7. Different substances have different Henry's law factors. Okay? So we're going to look at problem 13.2 on page 555, which is a Henry's law problem. So 552. Guys, I apologize. problems across the whole page, so it's not as easily projectable as I would like. So I'm apologizing in advance. Okay, if we look at problem 13.2, this is one of the practice problems. It says, determine the solubility at 25 degrees of air at 1 atmosphere, assuming, determine the solubility of oxygen in water, 25 degrees exposed to air at 1 atmosphere of pressure. Assume the partial pressure of oxygen is 0.21. So in this problem, we're asked S the solubility. And we're given our temperature is 25 degrees C, and we're dealing with oxygen, and the pressure for oxygen is 0.21 atmospheres. Now we're going to have to look up the Henry's law. The Henry's law. K factor. Okay, and we're going to work off the equation S equals K times P. Now I'm going to flip over so that we've got our chart again. Now for oxygen, K is 1.3 times 10 to the minus 3. So this is 1.3 times 10 to the minus 3, and we looked it up. Okay? So let's shift over to my board. So really, all I have to do here is plug in. S is going to equal our K factor, 1.3 times 10 to the minus 3, and that has units of molarity over atmospheres, times our partial pressure of oxygen, which is 0.21 atmospheres. Notice the total pressure, the temperature of 25 degrees and the total pressure is kind of extra information. The 25 degrees helps us because our table was for 25 degrees. So if I solve this, I have 0.21 times 1.3 exp3 negative. So the solubility is 2.73 times 10 to the minus 4 molar. Notice the atmospheres and atmospheres there divide out. Okay, so there's a Henry's law problem. Those are hopefully what you consider to be easy. Okay. Now, pressure really doesn't play a role in the dissolving process of solids, liquids, or liquids and liquids. Really, it's only important when we look at gases in liquids or gases dissolving in solids, because remember that the density of a liquid and the density of gas is quite high compared to that. Density of liquids and solids is quite high compared to that of gases. In other words, they're not very compressible. Okay, so squeezing them doesn't really help. Okay guys, we're ready for colligative properties. So that's the end of chapter 13, lecture 1.